Hello everyone, welcome to the third episode of this series. In this video, we'll talk about row echelon form and Gaussian elimination. Before we begin, I just want to point out that in mathematics, when we say something is unique, we mean that it is exactly one of that kind. In other words, if there is a linear system which has a unique solution, that would mean that the system has exactly one solution. Okay, so last time we talked about elementary operations and augmented matrices. And this time we are going to uh, first define some systems that can be easily solved. And what I'm referring to is the row echelon form, or the systems that correspond to the row echelon form of matrices. We're going to talk about an algorithm for picking which elementary operation to use. Um, and we'll be dealing with systems that have no solutions or multiple solutions. Okay, so matrix is said to be in row echelon form. We abbreviate it as REF if the first non-zero entry in each row is a 1, and we call it a leading one. And each row begins with more zeros than the row above it, or all zeros if this is impossible. So let's look at some examples. So all of these matrices are in row echelon form. So let's look at the first matrix. Look at each row. Each row has a bunch of zeros followed by a bunch of non-zero values, where the first non-zero entry or the first non-zero value is 1. And as we go down, the number of zeros keeps increasing before we get to the first non-zero value. The same thing happens here. There are no zero values here, then there are 2 zero values here, and then there are 3 zero values here. But the first entry is always 1. The first non-zero entry after a bunch of zeros. In the last one, we have no zeros here, we have 2 zeros here, and then we have 2 rows that are entirely 0. So because of the second condition, if we have 0 rows in the reduced echelon form, they will always appear at the bottom of the matrix. And these are some of the non-examples of row echelon form. In other words, these are the matrices that are not in row echelon form for the following reasons. So the first matrix has a 0, but then the leading term is not 1, it's 4. And therefore, this is not in row echelon form because it contradicts the first condition. The second matrix is not in row echelon form because you have 3 zeros before we get to a non-zero entry in the second row, but in the third row, you only have 2 zeros before we get to a non-zero entry. And this contradicts the second condition. This would have been in the row echelon form if we had switched row 2 and row 3 with each other. Now, for a similar reason, the third matrix is not in row echelon form because this row made of zeros is above this row that has a leading term. So as I said a moment ago, that a row made up entirely of zeros should be at the bottom of the matrix. So if we were to make it a row echelon form matrix, we would switch rows 3 and 4 with each other. So here are some additional properties of REF matrices, row echelon form matrices. So any rows of zeros must be at the bottom, something I said earlier. Each leading one is to the right of the leading one above it. This comes directly from the second property of the definition of row echelon form because it's completely dependent on how many zeros are present in a particular row before we get to the first non-zero entry. And each column can have at most one leading one. Again, the same idea. So if an augmented matrix is in row echelon form, then the system of linear equations corresponding to it is very easy to solve. And we're going to consider three cases. There will be a case where the system has no solutions. There will be a case where the system has infinitely many solutions. And then there will be a case where the system has a unique solution. So we'll start with case one. So let's say we have a system where one of the conditions hold, all of the three conditions are equivalent, and if one of them is satisfied, the other two are as well. So the three equivalent conditions are as follows: that one, there is a leading one in the right column of the augmented matrix. In other words, the column that corresponds to the constant terms in the augmented matrix. Which is the same as saying that there is a row that is entirely made up of zeros before the divider line in the augmented matrix, and then you have a one, which is the same as saying that if we were to convert this back to a system of linear equations, we would get a linear equation in that system of this form: 0x1 plus 0x2 dot 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 plus 0xn equal to 1. But this just means that 0 is equal to 1, and that is a contradiction. So in other words, that the system of linear equations is consistent and this system has no solutions. Otherwise, the system is always going to be consistent. So if you have an augmented matrix in row echelon form that doesn't satisfy any of these three conditions, the system is going to be consistent, so it's going to have at least one solution. Let's look at an example. So this is an augmented matrix, and we see that there is a row of the form 0, 0, 0, and then 1 in the right column. So it is exactly what the second condition says. So now when we convert this back to a system of linear equations, we get x plus 2y plus 3z equal to 1, 0x plus 0y plus 1z equal to 2, and 0x plus 0y plus 0z, which is 0, equal to 1. Now 0 equal to 1 is not true, and therefore there are no x, y, and z that are going to give me 1 in this third condition. So the system is inconsistent as it has no solutions. So let's move to case 2. So let's assume that our matrix is in row echelon form, and there is a leading one in each column except the rightmost one. That means before the divider line in or the separator line in the augmented matrix, every column has at least one leading one, which means there is no like row of zeros before the separator line. So if that is the case, we turn the augmented matrix into a system of linear equations, and we start at the bottom equation, and going up, we solve each equation for the variable with the leading one. An example is going to make this clear in a moment. And this always produces the unique solution to the system. In other words, the system is going to have exactly one solution, and we will find that out algorithmically by the second step. So for example, we have this augmented matrix in a row echelon form. So you have like leading ones in each row, and the number of zeros before the first non-zero entry keeps on increasing as we go down. We convert this into a system of linear equations. So the first row becomes the equation x plus y plus z equal to 1. The second one becomes 0x plus y plus 2z equal to 3. And the last one becomes 0 plus 1z equal to 2. So what this second step means is that we start from the bottom equation and we keep finding values. So the bottom equation already gives us a value for z, that z equal to 2. Then we take the z equal to 2 and we plug this in the middle equation, and we get y equal to -1, because we get the y plus 2 times 2 equal to 3, so y has to be -1. And now we have values for z and y both, so we take these and we plug them in the first equation, and then we solve for x, and in this instance we get that x is 0. So the triplet 0, -1, 2 is the unique solution to the system. Now let's move to case 3. So case 3 happens when some of the column don't have leading ones. So in that scenario, we turn the matrix into a system of linear equations. We pick a parameter for each variable whose column doesn't have a leading one. Letters S and T are popular choices. You can use letters U and V. You can use some of the Greek letters if you want. It's all fine. And then starting at the bottom equation, we go up and we solve each equation for the variable with the leading one. And every solution to the system will be of this form. In other words, there are going to be more than one solutions. There will be a family of solutions, and it will depend on the variables that we have introduced in step 2. Let's look at an example. So we're given this matrix in row echelon form. So the first 2 rows have leading ones, and the third row is made up entirely of zeros. So it is indeed in row echelon form. So we first convert this into a system of linear equations. So the first row becomes x plus 2y plus 3z equal to 0. The second one becomes z equal to 2, and the third one becomes 0 equal to 0. So it doesn't really contribute anything. So the column corresponding to y, that is the second column, doesn't have a leading one. So by our algorithm on the previous page, we set y equal to s, where s is my parameter. So once my y is s, and because from the second equation I know that z is equal to 2, we get that x is -2s minus 6. I just plugged in the values of z and y as 2 and s respectively, and then I solved for x in this first equation. And now every solution will be of the form -6 minus 2s s2. So like this triplet is going to be a solution for every real value s. So to summarize, if there is a leading one in the right column, the system is inconsistent and has no solutions. Otherwise, turn the matrix into a system of linear equations. Pick a parameter for each variable whose column doesn't have a leading one, like we did in the previous example, and then start at the bottom, keep going up, and solve for each equation for the variable with the leading one. Now, this process of starting from the bottom and going back up is called back substitution. And intuitively, each equation is used to find the value of the variable with the leading one, and any leftover variables can be freely chosen. So in the previous example, we found the values for x and z using the back substitution method, and the value of y was chosen freely because it had no leading one in the column corresponding to it in the augmented matrix. In the last episode, we talked about elementary operations on augmented matrices or systems of linear equations, and how these operations preserve the solutions of these systems. So the 3 elementary row operations are the following. You exchange 2 rows, you multiply one row by a non-zero number, or you add a multiple of one row to another row. So we're going to learn that we can use these elementary row operations to convert any matrix into its row echelon form. And if we can actually do that, then we can find solutions easily, because of the three cases we learned, to any original system of linear equations. So this process of converting augmented matrices into their row echelon forms is called Gaussian elimination. And the wake strategy is as follows. So we start with the top row, and while going down, we create a leading one in the leftmost possible column and kill all entries below it and repeat the process. And I know this sounds vague, so let's move to more explicit steps in the algorithm. So if the matrix consists entirely of zeros, stop. This is almost never going to happen. Otherwise, find the leftmost column with a non-zero entry. If the top row has a zero in that column, we can switch rows because that's one of the elementary operations, and we can fix this. Once we are done with step 2, we turn this leading number into a leading one by multiplying that row by a number. Remember that this is also an elementary operation. And then by the third elementary operation, we make each entry below the leading one into a zero by subtracting multiples of the top row. So the top row is now fixed. So we repeat these steps on the remaining rows and we ignore the top row. And it's easy to use on a computer, but we're going to see an example by hand for full understanding of the algorithm. So we're given this exercise. So we have this augmented matrix and we want to put this into a row echelon form and then find all solutions to the corresponding system of linear equations. Okay, so we first look for the leftmost column with a non-zero entry, and that's column 1, because column 1 has at least 1 and 2 and they are non-zero. Now the top row in this column already has 1 in this column, so we can we can skip step 2 and 3 because it's non-zero and it is already 1, so we don't need to turn it into 1. Now we move to step 4, which is we use this 1 to make everything below this 1 a 0. So we multiply this row by -2 and then add it to the second row. We don't need to do that to the third row because in this column this is already a 0. So we multiply row 1 with -2 and add it to row 2, and when we do that, this is what we get. Now the first row is fixed. Okay, so now we ignore the top row and we look for the leftmost column with a non-zero entry. And because we're ignoring the top row, this leftmost column would be column 2. And now the new top row, ignoring the top row itself, has a -1 in this column. So the second row is the new top row. And this has a -1 in column 2. So we convert this into a 1 by multiplying the entire row 2 by a -1. So we have a leading 1 in row 2 now. So the next step is to turn all entries below this leading 1 into zeros. So we do so by multiplying this row 2 with a -1 and then adding it to row 3. So when we do that, we get 0 and 3 and 1. And now the second row is also fixed. So now we ignore the top 2 rows and we look for the leftmost column again with a non-zero entry. And there's only one column left, that's column 3. So this new top row, which is row 3, has 3 in this column. So we turn this 3 into a 1 by multiplying the last row by 1/3. So now this augmented matrix is in row echelon form. So we convert this into a linear system and solve it using back substitution. So this matrix now becomes the system of equations. So we get x plus 2y minus 1 equal to 1. We get 0 plus y minus 1 equal to 0. And we get 0 plus 0 plus 1z equal to 1/3. So the last equation, the bottom equation, directly gives us z equal to 1/3. We take this value and we plug it in the second equation where we know that y is equal to z because y minus z is 0, and we get y equal to 1/3. And then we take these values of y and z, and we plug it in for the equation for x, which comes from the first equation here, and we get that x is 2/3. So we have explicit values for x, y, and z. So we get that the triplet 2/3, 1/3, 1/3 is the solution. In fact, the unique solution to the linear system. Great. So, like, I'm going to conclude here that we can find every solution to every system of linear equations by what we learned in the last episode and this episode. So in the last episode, we learned how to take a system of linear equations and convert it into an augmented matrix. And in this episode, we learned how to take that augmented matrix and put it into row echelon form using Gaussian elimination, and then turning it back into a system of linear equations and finding all solutions using back substitution. And as a note, if you encounter a leading 1 in the right column, you can stop immediately because there are no solutions, and we saw that earlier in this episode. One last thing I want to say is that a system of linear equations can only have either no solution or a unique solution or infinitely many solutions. And the location of the leading ones in row echelon form tells us which case it is. So this theorem about the number of solutions to an SLE tells us that you will never have like some arbitrary number of solutions. You will never have 5 solutions. If it's more than one solution, it has to be infinitely many. And with this, I would like to end this episode. Bonus points to you if you can associate this meme to something we learned in this episode. I will see you guys soon. Until then, happy learning.